Okay, somebody also came up with the relationship between M, R, and I for reasons that we spent plenty of time going over, and your book showed it, and reasons that are sort of documented in your multivariable calculus, where you actually integrate this expression over solids and so forth about arbitrary axes. Mass, distance from the axis of rotation, and moment of inertia. Okay, a particle of mass m constrained to distance r about the axis, or radius r about the axis, moving in a circular path about an axis. Moment of inertia is mr squared. This was derived from the consideration of the kinetic energy, work energy theorem, and so forth. But of course, we're having a little trouble with that one. Hopefully that goes away in the next 2 weeks. Okay, so this is what we have. That's the relationship here. It's totally fundamental. It has to be second nature. You've got to know it. You've got to carry it with you throughout your life. Okay. Then what do we have? We have F, R, and tau. Now first we recognize these as vector quantities. People first, I'm not sure how this actually went, but all three of these are vector quantities. And this is the first case where we have three actual vector quantities in a relationship. Now you can add two vector quantities to get a vector quantity, but you're not getting a new type of a quantity. When you add two vector quantities, they got to be like quantities. These are unlike quantities, and they're related by the cross-product relationship. Try to think of another relationship that would relate three vectors, and given three vectors, a relationship between those three vectors and only those three vectors, for which all three are actually vectors, and where none of the two are like quantities. You're not going to find one. Okay, I can't think of one. I don't think there is one, but I haven't really asked myself the question, but it's kind of worth noting. Okay, and the relationship is, well, first of all, identify. What's this mean? Somebody identified tau as torque. That's good. So what's F? Well, F is the force that's applied, and R is your moment arm. If you do moment arm cross force, you get your torque. Okay. And this is much more comprehensive and much simpler than just the scalar relationship, where torque is force times moment arm, or moment arm times force. Okay, if you do that with just scalar moment arm and scalar force, you got to be careful if you're just going to multiply them that the two are perpendicular, and you've also then got to ask yourself the question: is this counterclockwise or clockwise? Okay, and I gestured wrong. No, that's counterclockwise, that's clockwise, I gestured right. Okay, so you've got to know a lot, whereas with the cross product, well, you got to know a lot to apply the cross product, but then everything else that you need to understand comes right out of what you understand about the cross product, and you get the entire picture, and you don't have to worry about whether the angle's a right angle. If you got the two vectors, it's going to work. Then, and of course, if you understand the cross product, you understand why you have to have a right angle just to multiply the scalars and get the scalar torque and all that stuff. Okay? So you want to be sure you understand the nuances of this relationship. And then we have torque, moment of inertia, and angular acceleration. Now, I was a little bit surprised that people didn't immediately see alpha as angular acceleration, since you just had a test on rotational kinematics. But I noticed there were some things in that test that leave me less surprised than I would like to be. Hopefully by the time of the last exam we get this straight. Then there's the question of not only what does this mean, but what's a vector quantity and what isn't? Well, we know the torque is, and right there is a hint. If this is a triangular relationship, that is, if you can get any of these from the other two, then we know that both of these can't be scalars, because two scalars can't give you a vector, can they? So we have a hint that something has to be a vector. What is it? Well, moment of inertia isn't a vector. It's a scalar quantity obtained by multiplying mass by a square of some distance quantity. So it must be alpha. Well, don't we already know that alpha is a vector quantity? Okay, alpha is the rate of change of angular velocity. Angular velocity is a vector quantity. So alpha is a vector quantity. There are a lot of connections here. You want to think about why that's a vector quantity. Also by analogy with motion in 2 or 3 dimensional space, you know that acceleration is a vector quantity. And I'm observing right now that people, even though we've done vector quantities throughout multivariable calculus, aren't really relating what they do there, aren't really working in terms of vector equations, breaking the vector equations down into scalar equations before it's appropriate to do so. So I'm just kind of putting a plug in for doing things with vector equations. Anyhow, this is our relationship where torque is our analogy to force, our analog of force. Moment of inertia is our analog of mass, and angular acceleration is our analog of acceleration. This is just Newton's second law. Analogous to force equals mass times acceleration. But don't confuse I with mass. People did that in cases on the test. And just be careful how you think of this and how you apply it. But this is absolutely fundamental, as are a number of other essential relationships that we'll talk about in the future. I'd have asked you to go through the whole list and think through as much as you can, because we've got one more day to really go through this. And we're trying to summarize this. We're trying to bring the course into a nice whole so that you can proceed to the last exam and perform as well as possible in context of basic first principles.